Now let's take a deeper look into the mechanism of EAS nitration. So as mentioned earlier, nitration always has to proceed through the creation of a strong nitronium ion electrophile. So a nitronium ion electrophile looks like this. It's going to be an N with a double bond O at the top, double bond O at the bottom, and a positive charge. Why do you think that's going to be a strong electrophile? Guys, it has a full positive charge. That's one of the strongest electrophiles possible, okay? That's the perfect type of molecule that benzene wants to react with, okay? Now remember that we said there's two different common ways to generate this nitronium. You could use concentrated nitric acid by itself. By the way, heat never hurts. Heat's going to help this reaction regardless of what reagents you're using. Or you could also just use nitric acid and sulfuric acid together. So I included both of these in our mechanism just so that you guys can see how they're really the same exact thing. So in this mechanism, we have one equivalent of acid reacting with another. Regardless of which acid it is, they really do the same thing. One is going to be a proton donor, and one is going to be the base. Okay? With the sulfuric acid and the nitric acid, that makes sense. Sulfuric acid is a much stronger acid than nitric acid. So it makes sense that sulfuric acid is going to be the proton donor. Now for nitric acid, we would just imagine that at equilibrium, some of this nitric acid is going to be donating protons to the other. Okay? So let's go ahead and see exactly which part of the nitric acid would be basic. And it's going to be this oxygen here with the lone pairs. The reason being that you're going to see later on it's going to become a great leaving group. So we would have that if you're proceeding through sulfuric acid, that this oxygen would grab one of the hydrogens on sulfuric acid, but you could also do the same thing, guys, for nitric acid up here, okay? It's going to have the same net result. What we're going to get is we're going to wind up getting, here's our benzene ring, I'm just bringing it down, and now we're going to get nitric acid that looks like this. It's protonated. It's now going to have two hydrogens on that oxygen. And that has just created a water leaving group, okay? So in order to generate the nitronium ion, all I have to do is eliminate with the O negative. So what I can do is I can do an elimination reaction, bring down, make a new pi bond, and kick out the water leaving group, okay? What this is now going to give me is a nitronium ion plus water. Cool? Now I can go ahead and I can do the rest of my mechanism. So at this point, benzene, I've had to bring it down a few times now, I'm drawing too much. Benzene is going to attack my nitronium ion. What is that going to look like? It's going to do this. By the way, positive, yeah. It's going to attack the nitro, or the N, and then it's going to kick out one of these pi bonds and make them into a lone pair because you have to break a bond. This is going to lead us to our sigma complex, right? So let's draw our sigma complex. I know it's a little annoying, but you guys should get practice with it. So now this is NO2, right? And we've got double bond here, positive charge, and now we've just got to draw the whole complex. So I'm going to move it over. I'm going to move it to this location. And now this is my last resonance structure. All right, so we're done with the sigma complex. There we go. That's our full resonance structure. Now, what are you going to use as the conjugate to eliminate this hydrogen? Remember, we have to do basically what's a beta elimination on this hydrogen. Beta to the carbocation. And even though you totally could use the conjugate of sulfuric acid, so you could use the negatively charged OSOH4, I think I said that right? Whatever, I could write it down correctly. But actually, we're not going to use that because typically most textbooks and most professors are actually going to use the water that left in the nitro group, okay? And it really doesn't matter, guys. You could use the water. If you want, you can use the conjugate base of the acid that you used. I don't really care, but just typically it's the water that's used in these reactions. It doesn't matter because in the end of the day, this would make HO3 plus, which is just basically aqueous acid, so it doesn't matter. So I'm going to go ahead, come down, and eliminate my H, and put the double bond there, and we get our final product. And what our final product is going to be is it's going to be our nitric acid. It's going to be our nitro group, nitrobenzene, okay? Plus we're going to get H3O plus. And, then you would get, I guess, the conjugate of your sulfuric acid if you had used that, which is OSO4H negative. OSO3H. Okay? Awesome, guys. So that's it for the nitration mechanism. So let's move on to the next reaction.